What is going on, guys? Welcome back. In this video today, we're going to do a technical deep dive into Kimi K3, which means we're going to take a look at the architecture and mathematics behind it. This is not going to be a 1-hour video where we talk about this in a very extensive manner. I just want to explain to you what is happening behind the scenes, what the architecture of Kimi K3 is, because this is an open weight model that at the very least approaches the state of the art, if not defines it, because it does outperform Fable, at least on some metrics. So what we're going to do today is we're going to take a look at the architecture. I want to explain what is happening with Kimi K3 behind the scenes, how does it actually work, and the reason we want to know this is because it's nice to be up to date on the state of the art. You want to understand what is happening, what is the best practice, which techniques are the most promising, and also the next time a model is released and you see certain elements being used there, you can compare it to something like Kimi K3, for example. So depending on how you guys take this video, how much engagement there is with this video, I'm going to make this more often for the various models that are going to be released, for the various open models that are going to be released. So if you like this video, let me know by hitting a like button and subscribing. And now let us get right into it. Alright, so we're going to do a technical deep dive into Kimi K3 in this video today, the open weight model from Moonshot AI, which is at the very least approaching state of the art, if not defining it. You can see the benchmarks here, oftentimes ranking number 3, number 2, sometimes ranking number 1, outperforming both GPT-5.6 Sol and Fable 5. Also for the other benchmarks here, you can see sometimes Kimi K3 ranks ahead of both of them, or at least one of them. Also, if you go to the LM Arena, formerly called LM Arena, nowadays arena.ai, you can see Kimi K3 oftentimes ranks 4th, 3rd, but if you go to code and web development, for example, you find it in spot number 1, ahead of Claude Opus 5, Claude Fable 5, GPT-5.6 Sol. So this is really a powerful model that is going to be open weight. Now we have the 27th of July, roughly 3 p.m. Central European time. So anytime we might see the actual model weights, and then this would make it an official open weight model. But what I want to talk about in this video today is not just comparing benchmarks, not telling you it's good. I actually want to talk about the architecture. I actually want to go deep into the functionality, into the behind the scenes of Kimi K3. So we're going to take a look at this here and we're going to explain it. I want to explain what is happening here behind the scenes. And I want to do this in a quick and simple way. So we are going to get mathematical and technical, but I don't want to make this a 1-hour video where I just ramble and everything's super complex. I'm going to try to keep it simple and intuitive. So what I'm going to do now is I'm going to make a screenshot of this and I'm going to open this in my favorite visualization tool, MyPaint, where I'm going to be also writing stuff in addition to it. So this is the architecture of Kimi K3, and in order to understand it, you need to understand that not everything is released in this blog post here. On two levels, on the one hand, not everything is released yet because there is more information about the training process, about the architecture and everything that is going to be shared with us. That is one part of it. The other part is that not everything in this architecture is new. Some of the stuff was already released before. For example, here, Kimi Linear. This paper introduced the Kimi Delta Attention, KDA, that we're going to talk about. This paper here, Attention Residuals, is also part of the architecture or defines part of the architecture. And latent MOE is not exactly part of the architecture because we're using stable latent MOE, but the idea for the most part is quite similar. We do have some additional stuff for stability. But before we start with any specific detailed stuff, let's just decipher this graphic. Let's just make it simpler to understand. So what you see here is basically the most important part. This rectangle here is a block. So that is our block number n. And what you see down here, block n-1, n-2, n-3 is basically just repetitions of the same structure. And here you can see that this part here is repeated once and this part here is repeated 3 times. So basically you do 3 of those and then 1 of those, and that's a block, and then you have n blocks, starting with the embedding layer, and then you get to all the different blocks up until block n. That is the basic structure. What you see here on the left is just a zoom into the individual components. So you have stable latent MOE, stable latent mixture of experts, which is happening here. This is what it looks like. We're going to talk about this as well. And you have KDA, which is Kimi Delta Attention. This is what you see here. And we're going to talk about this as well. And then you have also Attention Residuals, which is what you see here. And we're going to talk about this as well. So these are the 3 things we're going to talk about. We're going to talk about KDA, Kimi Delta Attention, stable, latent, MOE, and attention residuals, because these are the interesting parts here of the architecture. And I want to start with KDA because I think that's easy to understand and it's also interesting to understand. And what you need to understand about KDA is that this is how Kimi manages memory. So we're all talking about memory here. You can think of this to be a little bit like a recurrent neural network where you have forgetting mechanisms and you want to remember stuff, you want to forget stuff over time, you want to forget specific stuff. Basically, this is the way that Kimi manages its memory. And it does that with a formula that defines the current state. So this formula, when you see it the first time, might be confusing, but once you understand the components, it's quite obvious. So I'm going to write it down first. ST is the current memory state, or the memory state at time t. This is the result of taking the identity matrix minus a parameter beta at time t, because this is input dependent. And then you have KT, which is the key, KT transposed. That whole thing times the diagonal, let me rewrite this, diagonal, given something, a vector alpha t, which we're also going to talk about here in a second, times the state of the memory at time t minus 1 plus beta t, KT, and value t. And of course, we need to transpose this as well. So this might sound, or this might look confusing, but you need to understand what is happening here. Basically, you have the new memory state, new mem state, and the old mem state. And then you have two mechanisms. You have the vector, which is for channel-wise. Let me write this down. This is for channel-wise decay of memory. So the idea is that the input, because alpha t and beta t, both of those are defined by input. So they are determined by input. There is a learned transformation that takes the token input and turns it into alpha t, which is a vector, and beta t, which is a number. And these two variables determine how much we forget and what we forget. So here we have channel-wise decay, which means that if you take a diagonal, this is the operator, if you take diagonal of some vector x, y, z, let's say we have 3 channels here, that is going to turn this into a matrix where the diagonal is x, y, z. So we will have x, y, z, 0, 0, 0, 0, 0, 0. That is basically the matrix we end up with. That's the thing we're doing here. And basically what we're doing with alpha t is for every channel, we're just defining the decay. How much should the knowledge in the various channels decay from this old memory? And in addition to that here, we specifically try to forget targeted information that aligns with the dimension, with the direction of KT. So we try to forget the information stored at address KT. You have to think of this in embedding space with the intensity, the forgetting strength or update strength, you could say. Let's call this update strength. We're trying to forget targeted information. This is why we do identity matrix minus that to make it erase that basically. So we're taking this, we're forgetting part of it with a certain intensity, and with the same intensity here, we're learning the new value. So we have key, and we have key and value. So we're forgetting what's already there to some degree beta, and we're writing the new stuff that we want to write there with the same intensity beta. And overall, we still do some forgetting here with alpha, which all of those are determined by inputs. And this is also what you can see here in the Kimi graph, because basically the graphic here is we get token inputs. So these are tokens that flow into this attention cell. And what happens here is we feed the tokens through a linear layer, 1D convolutional layer. Then we have the action activation function that I now forgot. It's not ReLU, it's SILU, S-I-L-U. Yeah, there you go. This is the name, the sigmoid linear unit, also known as the swish function, which is basically not a ReLU function, but quite similar in terms of most of its properties, but it's smoother and easier to work with. So that is the swish activation function here, this little thing, and we have it here as well. Then we have L2 norm, and basically what we get out of here is the query T and the key T. So you can see we have 2 layers here. This gives us value T, this gives us alpha T, this gives us beta T, and this gives us the output gate, which is, I think it was GT. So this is just a thing that we multiply here. You can see those are all sigmoid activation functions. So these values are mapped between 0 and 1. And basically this is again for our global channel-wise decay. This is for the targeted replacement, and this is just for controlling the output here with this combination, with this multiplication here. But that is the idea. So we do all these mappings. Here we just have a simple, we feed a token in, it's mapped down into a smaller dimension, mapped back up into a larger dimension, sigmoid activation function. And here we get a vector, here we get a number, and all of this is fed into Kimi delta attention, which is this formula here. The new memory state is the result of doing this channel-wise forgetting from the old state and also targeted replacement of a specific address with the new value with a certain intensity beta t. I hope this is not too confusing, but this is one part of the architecture that Kimi uses to manage his memory, to selectively forget stuff, to forget specific channels, to replace information in an efficient way. This is Kimi delta attention. This is the KDA part here that we repeat 3 times with stable latent MOE. Which brings us to the next thing, stable latent MOE. Stable latent MOE is basically just mixture of experts. For those of you who don't know what mixture of experts is, the basic idea is we have, like here, multiple experts, but instead of using all the weights, instead of using all the connections, we choose a couple of them and we only route the tokens through those chosen experts, which saves compute. Now, usually it doesn't save VRAM because you still need to load everything into VRAM, but you don't have to do inference on all of them, which saves compute. And what you can see here is an interesting architecture, because what we have here is we have a bunch of routed experts, 1 to n. These are routed experts here, as you can see, and those are in total 896. We have 896 routed experts, 16 of which are always active at the same time. So that's a little bit less than 1.8%. And that means that what is happening here is, again, tokens flow in, and the raw tokens without any mapping are fed into the router. The router decides which of these experts is going to be active, 2, n, 7, whatever. We choose 16 experts that are going to be active. And we also feed the tokens always into shared experts. Now, according to this graph here, it seems like there's always 2 shared experts. Maybe that's not the case. Maybe there are more. We need to wait for more details. But as it looks right now, we have 2 shared experts, which are always consulted. So we always feed the tokens without mapping, without anything else, into those shared experts. And we also feed the tokens raw into the router. However, when the router decides that certain experts are going to be activated, before we feed the tokens into those experts, we map them down into lower dimensional space. This is why it's called latent MOE, because we reduce the dimensionality. We do all this inference here with a smaller dimensionality. Then we add everything together. We do an element-wise addition. We norm everything, and then we map it back into the higher dimensional space before we then combine everything with the output from the shared expert, and then we feed it into the next layer. So this is what's happening here with a stable MOE. This reduces the computation. First of all, of course, because it's MOE, mixture of experts, because we only route to specific experts. We have very, very sparse activation with 1.8% of the experts actually being active. And also we're reducing the dimensionality, which makes things easier to handle. And by the way, because I forgot to tell you how to compute the actual output of Kimi delta attention, what of course we need to do here is we take the memory state that we now have, the new memory state. The output at time t is going to be the memory state at time t transposed, and then the query vector, because that is our request, so to say, and this is now the information that is updated using the keys and the values. So we write our value into the position with intensity beta. We forget the current value. Before we do that, we do channel-wise forgetting. Then we have a new memory state, and then we query that memory state to get the actual output, just so we know what we're feeding into this stable latent MOE layer. And the reason we call this stable MOE or stable latent MOE and not just latent MOE is because we have certain things for stability, for making sure that the GPUs all get roughly equal work and the experts as well. So for the GPUs, we have balanced expert parallel training. We just make sure that the GPUs get roughly equal work. I think the details are not yet released. Maybe I'm wrong about this. Let me know in the comment section down below if you know the details for this one. But for the experts, we use something called quantile-based load balancing. So instead of having, let's say, 5 experts, and then I have some work 1, work 2, work 3, This is now a bad example. I don't think that this is a very good example. But instead of always saying, okay, which expert is the best to handle work 1, we don't do that because that might mean that this expert here and maybe this expert are always the best of handling all these different packages. So what we do instead is we have for each expert the top 10% of things that this expert should process. So the best scoring share of tokens, and only those are routed to the expert so that every expert can be utilized. So we define, for example, the top 10, only the top 10 of these tokens are going to be assigned to this expert. So even if for this workload here, this expert would be the best, maybe the best workload that this expert can handle is actually W2, we would route it here. That is in a nutshell what we're doing. So we're not just asking who's the best expert to handle this workload, we're asking which expert has this as their favorite task, you could say, as one of their favorite tasks. And then finally here we have the attention residuals. Now residual connections in general are used in deep neural networks to feed information forward without processing. So we have a cumulative thing that we're always passing along without doing the calculations here from the different or using the different cells. What we do here is different. We're using attention residuals. So we're focusing on specific information from the past. As you can see, each block here sends the information forward into the future, if you want to call it that. And our attention mechanism here is based in every layer. We have a pseudo query vector. So this is a pseudo query vector, we can call this, which basically describes what this layer is looking for. And this is learned, so this is not something that we statically code in. This is a learned pseudo query vector, which basically says this layer is looking for a certain type of information. So with this pseudo query vector, we find from all the previous blocks and also from the previous layer here, we find the most relevant information based on this query vector. We get the softmax function, so the softmax ranking, because we basically compute a score for each previous hidden representation produced by the various blocks here and by this previous layer. And then we can selectively look up information that is relevant for this specific layer that we're working in. And as you can see, whatever we have here is never fed directly into the next layer. So we have KDA here, but KDA is actually combined. So we're actually adding together here the residual output here from the previous layer, and then we're feeding that into the next layer directly, but we're also feeding that into the softmax function with the pseudo query vector, and only then does it reach the stable latent MOE or the gated MLA and so on. So these are, to keep it very simple, and then of course what we have here is a weighted sum. So we have a weighted sum based on this softmax activation. But this is basically the whole idea behind Kimi K3. Of course, more information will be shared, but I tried to condense it down. Of course, this requires some understanding of at least linear algebra to some degree and transformers to some degree. But to summarize here, Kimi delta attention is how we manage memory. We have the token inputs, we produce query and key vectors, we have value vectors, we have alpha t, which is for channel-wise decay overall. We have beta t, which is the update strength, so we replace the old knowledge with a new knowledge. And then we have the output gate, which just controls the output by using this element-wise multiplication. We have stable latent mixture of experts, where we have 16 active out of 896 total routed experts. So the router gets the tokens that we feed in raw to decide which experts are going to be consulted. We also have 2 shared experts, which also work with a full dimensionality. And then those 16 work with a lower dimensional embedding. We then map it back into high dimensional space, combine everything, that feeds it further. And for every layer, we use attention residuals. So we have residual connections, and we never feed something directly into the next cell. We always use the pseudo vector to specifically look up interesting and relevant information. Then we do a softmax scoring, and then we do a weighted sum that the result is then fed into this cell. So that's it for this video today. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. Let me know if you want to see more videos like this one, more technical deep dives into architectures, into state-of-the-art models. Let me know if you want to see the explanations on a simpler level, less mathematics, less architecture, more prerequisites that I explain from scratch. If you want to see it faster, if you want to see it slower, let me know in the comment section down below. Also, in case you're interested, on my website, you will find a services tab and a tutoring tab. There you can contact me if you need help with a project, if you need a freelancer, or if you want me to teach you one-on-one. Besides that, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.